I will start now. Okay, so my name is Juanjuan Huang. I'm a PhD student from Technical University of Munich, Physics Department. So thank you very much, Jerry and Matt, for organizing this very nice event. And also thank you for giving us a chance to present our work. Also, thank you, all of you, for participating and listening to the talk about energy dispersive X-ray absorption spectroscopy at the Munich Compact Light Source, which is a laboratory X-ray beamline facility based on inverse Compton scattering source. So this work is supervised by senior scientist Martin de Hoff. He's also here today, and our professor Franz Pfeiffer. So the talk today will be mainly divided into two parts. The first part, I will talk about the principle, the history development, the instrumental layout and properties performance of the source and the facility. And the second part, I will combine the properties of the source and explain why these properties are beneficial for such an energy dispersive XAS setup. Meanwhile, I will also show how was the data analyzed and some results of some standard sample. And in the end, I will show you some more recent in situ measurements, which was done in collaboration with chemistry group in our university. So before that, I will also give a very short introduction. So about X-ray absorption spectroscopy, this technique, I don't need to introduce too much as all of you are already experts in this field. So basically this technique can provide us a lot of chemical structural information. And compared to other techniques such as crystallography, which needs crystalline sample. This technique, we don't need any crystalline sample, and it's also applied to disordered systems such as gas phase or solution phase. Because it's an X-ray technique, so it allows us to selectively study certain elements that we're interested in the chemical system. So this makes this technique a very important and specific technique. This figure shows the paper related to X-ray absorption spectroscopy per year. The number has been significantly increased for past decades. Actually, before 1975, there was already pioneering XAS in 1931. However, it was until the arrival or development of synchrotron radiations in 1970s that this technique started to be widely applied to different scientific fields. Yeah, so currently most of XAS are carried out in synchrotron. Therefore, the number of papers related to XAS can be even higher if we have more synchrotron or other facilities where this technique can be done. That's why there've been a lot of efforts developing laboratory setups, such as the one with X-ray tubes. So, for example, this one from Jerry's group in Washington University, and he also gave talk in this XAS Journal Club. And these four are European groups, and also there are many other very good work that have been done. But I'm sorry, I cannot include all the papers here. And for other laboratory sources, there are, for example, laser-produced plasma source, high harmonic generation source, potassium source. And these three sources are currently mainly focusing on ultra-fast pump and probe studies. And for higher X-ray energies, inverse Compton scattering source, on the other hand, can generate high flux at higher energy. There are also many groups developing this kind of source nowadays, but so far it's mainly applied to biomedical imaging. And that's why we want to explore the potential of this source to be applied in X-ray spectroscopy field. So I will start with the first part. And for this part, I want to start by asking a question: how do we shrink a synchrotron? So for example, if we have a big synchrotron, let's say with a storage ring circumference of roughly 300 meters, if we want to shrink that to several meters, this requires the electron energy to be reduced from giga-electrovolts to mega-electrovolts. And these are typical parameters of undulator in the synchrotron. When reducing electron energy, this means the gamma factor needs to be reduced by a factor of 2. And this is the angulator equation. So according to this equation, if we still want the X-ray energy to be unchanged, let's say 1 Armstrong, this means that the angulator period has to be reduced by a factor of 4. That means angulator period in micrometer is needed. However, in current synchrotron angulators, permanent magnets are technically limited to centimeter scale. So how can we get an alternative angulator with shorter period? The answer is to use the magnetic field of infrared laser as laser angulator. So using this idea, such compact synchrotron can be built in a lab. So now I'm gonna show you a timeline to explain a little bit the history. So actually this laser angulator concept was already there in 1992. And then 6 years afterwards, in Slack, the mini storage ring concept was coming out, the compact light source concept. And 3 years afterwards, Lingshen, this company was founded to start to build the first commercial prototype of compact light source. In 2006, they observed the first X-rays from the compact light source. And since then, they have done some crystallography work. And during the period of 2009 to 2015, some previous PhD students from our group, they went to California and have done some grating-based phase contrast imaging work. Because there are quite some nice results with the source at that time. There was a decision and a funding during this time to get the source to be installed in Munich. So in 2015, the source has been installed at Technical University of Munich. And here I have some photos for you. So this was the room before the source was installed. And afterwards, there were some construction works. And in December 2014, this was the source shipping to Germany, to Munich. And in March 2015, the source has installed on the campus. But afterwards, the end stations and experimental hatches are still in design and constructing. So after the installation of the source and developments of end stations, since we are a biomedical imaging group, since 2015, we are mainly doing imaging related researches. Because of the different properties of the source, for example, partial coherence. So there are some grating-based phase contrast imaging, propagation-based phase contrast imaging work, which have done. Because of the narrow tunable spectrum, there was also angiography spectral imaging, which has been done. And microbeam therapy has also been done because it's high flux density. So then I will move on to introduce you the instrumental setup of the source. So first of all, electrons are generated in this electron gun, and then accelerated to several tens of mega electrovolts to this linear accelerator, which is roughly 5 meters. And then electrons are transported by this transport line into this mini storage ring, which has a circumference of roughly 4.6 meters. And you can see there are also some bending magnets and quadruple magnets in this storage ring. At the same time, another infrared laser is also produced and enhanced to a power up to 350 kilowatts in this laser cavity. And this laser collides with the electrons and therefore generating X-rays. The generated X-rays can be delivered into 2 experimental end stations, and these end stations are not part of the commercial system and have been designed and built by our group. Usually for imaging technique, we don't use, for full field imaging technique, we don't use any X-ray optics. Therefore, depending on X-ray beam size, which is needed. So for example, if a bigger beam size is needed, we go to the second hatch. So far, this hatch is small, but we will also plan to rebuild it and to fully utilize the space of the room. Now I will move on introducing the properties and performance of this beamline. The electrons and infrared are collided head-on-head. The electrons has a pulse length of roughly 50 picosecond, infrared photon 26 picoseconds, which gives rise to an X-ray pulse length of 60 picoseconds. So initially I introduced the principle by using a laser angulated picture, and this can be also understood as an equivalent picture of inverse Compton scattering, where the energy is transferred from the electrons to the photons. Yeah, the X-ray energy actually has an energy gradient. That means the more central the X-rays, the higher the X-ray energy. If we consider the X-ray emitting in a 4 pi full angle, this is the simulated spectrum. However, in this source, we sort of have a aperture which constrains the divergence to be 4 millirads and cuts off all this lower energy flux. And therefore, the bandwidth is much smaller, which is around 3% to 5%. And this is a measured spectrum of a 35 keV configuration. The tiny peak here is due to the fluorescence from the solder of the detector. This equation can describe the inverse Compton scattering process. And as you can see, the X-ray energy is proportional to the square of electron energy and laser energy, which is also shown in this graph. But the laser energy is fixed. The laser wavelength is fixed at around 1000 nanometers. So the X-ray energy is tuned by changing electron energy. Here I give you some example. So for example, this is a 15 keV X-ray spectrum and 25 keV X-ray spectrum and 35 keV spectrum. So currently the operating energy range is between 15 keV to 35 keV. And finally, I want to make a comparison between the MuCLS and the third generation synchrotron radiation, a rotating anode, and X-ray tube. So the total flux of the MuCLS ranges from 1 to 3 times 10 to the power of 10 photons per second. This is actually slightly lower than that of rotating anode. However, because of smaller source size and smaller divergence, we can reach brilliance up to 1.2 times 10 to the power of 10, which is slightly higher than that of rotating anodes. The bandwidth is 3 to 5%, which is more or less similar to that of synchrotron. The divergence is also much smaller than X-ray tube, which is 4 millirads. The source size is around 50 microns, and again, similar to that of synchrotron. And in the end, the cost and infrastructure is lying in between the large facility and the traditional X-ray tube. So to summarize, such facility based on inverse Compton scattering source is filling a gap between conventional X-ray tubes and synchrotrons. So all these properties has made the source a very special source, and therefore also made it very suited for an energy dispersive X-ray absorption spectroscopy study. Before moving to next part, I will make a pause here for questions so far.
Great. So yeah. So are there any questions from people so far? If not, I'll ask one. The infrared laser to basically sets up the wavelength for the undulation of the electron beam, correct? How tunable? What range of tunability do you have with the laser?
Okay, I will switch back. Oh, okay.
Yeah,
So for
maybe I
tuning,
missed that.
yeah, for tuning, so if you see this equation, so you can tune X-ray energy either by tuning electron energy or laser energy. But in our case, because we are using an infrared laser, and also, I mean,
Right, okay.
it's proportional to the square of electron energy. So we tune it by changing electron energy, and we keep the laser wavelength fixed, so we don't change the laser. Yeah.
Gotcha. Okay. Okay. I think Matthew has a question. Why don't you go ahead, Matthew?
Yeah, I was wondering if it might be possible to get down to 11 kilovolts and therefore be able to catch the platinum and gold edges and be able to do noble metal catalyst, which is popular.
So in principle, yes, it's possible to go down, to let the energy go down to even to 8 kV. But so far, it's like the flux drops a lot when we go to lower energy, because the divergence also absorbs some flux. But in principle, it's possible to go down to 11 keV.
Would a longer wavelength laser solve that problem?
This one I'm not so. This one I'm not so sure. Martin, can you comment on this? Maybe, okay.
Yeah,
that's possible. You could change the laser wavelength, and then you could shift the energy range. We are not so interested in this lower energy range for our imaging applications. We are mostly working with the higher energies. So we actually barely go to the 15 kV. And so the machine is not really optimized for getting the high flux out at the lower energies.
Okay,
so
it makes sense.
That's a question of exit windows and so on. But you could modify that to optimize it more for the lower energies.
Right. Okay, if there aren't any more questions, why don't you continue? This has been great. I love the graphics, especially, but continue. And
okay, yeah, sure. So I'll continue to the second part. So in this part, I'm gonna combine the properties that I introduced before and explain why these specific parameters are good for energy dispersive setup. So this part is based on the paper that came out recently. Yeah, so before talking about why is bandwidth suited for ZAFs, I can briefly introduce you the setup. A silicon wafer is placed 4 meters away from the source. The silicon wafer diffracts a Bragg spin in this direction, where we put a sample together with the CCD camera. And as an initial tryout, we chose a silver foil which has KH at 25.5 keV. And we tuned the MuCLS to a 26 keV energy configuration, and this is the X-ray spectrum of 26 keV. So it has a bandwidth of roughly 4%, corresponding to a full width half maximum of roughly 900 eV. And this one is a zoom in the spectrum of this middle part. The energy range that we use for silver ZEMs is highlighted in this purple region. And the energy range needed for XAS actually is similar to this full width half maximum. So this means the spectrum bandwidth is actually quite appropriate for XAS measurement, as it is wide enough for both ZEMs and XAS, and also narrow enough to avoid harmonic contamination. The divergence of the source, as I mentioned before, is 4 millirad. So this 4 millirad together with the flat or a slightly bent crystal wafer can give an energy gradient. So here is an illustration from top view. X-rays is coming from this direction, and crystal is rotated to a Bragg condition in a lower geometry. So this crystal plane can diffract a certain energy. Now, because of this 4 millirad, so the Bragg angles at these two different positions change a little bit. So giving a lower energy on the top and a higher energy at the bottom. This 4 millirate can therefore generate an energy ingredient, and this energy range window is very suitable for X-ray absorption spectroscopy. Now, if we put a sample and detectors in the bin, this one is what we can observe on the camera. This is the picture with highlighted X-ray beam path in experimental Hatch 1. So this one is the direct beam, and this is the lower diffracted beam, and this one is the sample, which is a silver foil. That was an old picture, and actually now we have a new crystal holder, and this crystal holder can bend the crystal by slightly pressing the edges. And the bending can be used to tune the energy range as well as the energy resolution, which I will show you some examples in the next slides. Okay, move on. Okay, yes. Okay, so using the setup, this is what we can see on the detector of this silver foil sample. So you can see this image is energy resolved in horizontal direction. For example, you can see KH here, and these fine fringes correspond to X-ray absorption fine structure. It's interesting that this image is not only energy resolved, but also spatially resolved. Here, I give you a better example of a 13 millimeter palette where I try to put some additional like tomb logo made of silver chemicals on it. And this is the image under this black diffracted beam. And this is again the KH of a silver element. Apart from that, the spatial information of the sample has been well reserved. For example, you see this tomb logo very clearly. The black beam is also tunable by tuning the crystal plane, crystal bending, asymmetry angle, and different geometries. So here I give you some example. This picture was obtained using silicon 111 plane of a silicon 100 wafer by a simple rotation without changing the crystal. So we rotate a little bit. The plane, crystal plane, can be rotated to silicon 311. And the energy resolution, total energy range is changed significantly. So you can see the fringes, the space between fringes is much bigger now. Also, there's another example using much less bend. In this case, the bending radius is 21 meters. And again, you see this big difference of energy resolution. So to summarize, depending on the experimental requirements, for example, this one can be used for XAS as it provides high energy resolution and short energy range. And for example, this one can be used for XAS as it doesn't need as high energy resolution as XAS, but needs a bigger energy range. Okay, so the data analysis is actually very straightforward. Here, I show you an example of taking a square region of interest. This X-ray image is taken with the sample. And then sample needs to be removed to take another I0 image. And by Lambert-Beer's law, an absorption image can be calculated. And then summing up all the values vertically, we can get a spectrum as a function of horizontal pixel. Then the pixel position can be calibrated into energy by comparing with synchrotron data. So in this example, I selected a square region of interest. And of course, a polygon region of interest can be also selected in order to increase the efficiency to make use of the whole beam. And again, because this is an image both spectrally and spatially resolved, and this spatial information can also be used as an constraint in image processing to improve the quality, spectral quality, without losing too much spectroscopy information. However, the beam size is very big, which is in centimeter scale. as different energies are shooting different parts of the sample. So such data analysis only applies to homogeneous sample. So now what about inhomogeneous sample? So for example, for such a very common ZAX sample, like a silver oxide pellet, which was mixed with boron nitride in order to reach optimal concentration. If we apply the same data analysis procedure, the final spectrum will be significantly distorted. However, However, we also came up with the idea to how to correct this concentration variation across the sample. So this image is taken at a crystal angle, rotation angle, let's say θ1. And this crystal rotation angle corresponds to the energy range around the kh of the silver. So what we can do is that to take another image with another crystal rotation angle, θ2, and this is slightly different than θ1. And when the Bragg's angle is changing, the energy range that's diffracted from the crystal will be shifted to a higher energy range. And in this energy range, we assume that absorption is a linear function without absorption fine structures. And this image here tells us the information of local concentration. And therefore, by a normalization of the first image to the second image, we can get a corrected profile. And you see that most of the artifacts, for example, here, are corrected. And even some tiny features like this line here, which corresponds to a spectral feature here, can be well reconstructed. Yeah, so before I show you some results of SIMS and what about the XAS measurements. So far, there are different options to extend the energy range to measure XAS. So the first way is to stitch two images at two different energy range, also by rotating the crystal. And the second way, as I mentioned before, as XAF doesn't require as high energy resolution as SIMS, the total energy range can be extended by using another crystal plane, for example, silicon 111. And the third way is to keep rotating the crystal in finer steps, and more images with different energy ranges can be stitched together. So using these methods, we are able to measure both SIMS and XAFs. Okay, the MuCLS has a relatively small source size, which is 50 microns. The energy resolution of energy dispersive setup is not so straightforward. And in this case, this was evaluated by a convolution of three factors: the crystal intrinsic bandwidth, the detector point spread function, and the source size. Actually, the source size is the dominant factor. And this table shows you some values of different crystal geometries and configurations. So for example, the silicon 311 plane of 11-meter bending radius crystal can give us energy resolution of 3.8 electrovolt at 25.5 keV, and this value is it's smaller than silver lifetime broadening, which is 6.5 eV. And the X-ray range energies, as I mentioned before, can be tuned by changing electron energy. So currently, we're able to tune it from 15 to 35 keV, and these are 6 different example source spectra, because these spectra are measured differently by 2 different detectors, so that's why the statistics look different. And this energy range can cover K ages of these elements and L ages of these elements. As most other lab XAS setup, they're more efficient at relatively lower energy, for example, 3D elements. So actually the MuCLS provides a complementary energy regime. But so far, we have only tried palladium and silver elements. Yeah, and these are some spectra of palladium and silver ZEMs compared with synchrotron data. So the dashed line here are measured in synchrotron in spring 8, and the solid lines here are the ones from MuCLS. Here we also have in homogeneous sample, for example, this palladium oxide, where we also did the concentration correction that I showed you before, and also other homogeneous sample like the silver palladium foil and silver nitrate solution. Yeah, the brilliance of the source is also much higher than a branch talon of X-ray tubes, and this enables a very efficient data acquisition. So this figure, I give you an example of a square region of interest by merging a different number of exposures and corresponding spectra. So even with only one exposure frame, the oscillation fringes here is still clearly resolved, and the statistics can be also improved by selecting a bigger polygon region of interest or by some image processing. And therefore, together with another I0 measurement, it's possible to still get good spectral quality with total exposure time of 1 minute or even less. Okay, so I will make another pause here for questions before going to the conclusion and outlook.
Okay, that's great. Yeah, so if anyone has questions, I guess there was a question about the energy range or whether there was enough for XAS, and I think you answered that well. Actually, I have a question about the energy resolution you get. That, if I understand, that will be a combination of the detector and the crystal like quality as you bend it.
Yes.
So what dominates that, and is that you know scale with energy as you go to lower energies?
You mean the energy resolution, the relation between energy resolution and the crystal bending, or?
Well, and also what dominates your energy resolution for this system?
Okay. So for example, in this example, the source size is the dominant factor, and of course, this maybe I can show you how. Oh, sorry, I'm sorry.
It's okay.
Maybe I can show you how the energy resolution was determined. So. Yeah, so basically like the source size detector, they give you this, like the source size, they give you this 50 micrometer, and to convert this micrometer to electrovolts, this is based on experimental data, I think here. So this is a illustration. So if you bend the crystal, for example, the Bragg's angle here change slightly, so that the energy range is also changed by this slight bending. And also the beam size is also changed, as an example I showed you before. And then, okay, wait a second. And then because you can measure how many pixels is the Bragg's beam covering. For example, in this case, it's 1,000 pixels. And then by calibrating with a synchrotron spectrum, you can also get the energy range. So in this case, it's covering 250 EV. Right. So we can get the experimental evaluation that for each pixel, the energy bandwidth is roughly 0.25 EV. And using this number, and this number also depends on different crystal bending, different crystal geometry, like different asymmetry angle, because all this contributes to different beam size and different energy range. So this number is then used here to convert this 50 micron or 9 microns into EV. And then in the end, in this case, the source size is the dominant factor of the energy resolution. I don't know whether this answers your question.
Yep, that answers the question. Yeah, that's good. Okay, so that's good. I don't see any other questions, and I might ask, wait till the end for any more. So please, people, think of some good questions, and why don't you continue?
Okay,
Really
sure.
Thank you.
Okay. Oh, sorry. Okay, I was here. Okay, so then I will make a conclusion. So to summarize the pros and cons of current XAS setup at the MuCLS. So it's a very easy setup as we only use a silicon wafer based on our already existing imaging setup. So this wafer costs less than €100. And the alignment is very easy. So the crystal can be removed when the hatch is needed for other X-ray imaging experiments or other experiments. And also the efficiency is good with good spectral quality. The source energy configuration is tunable and can be adjusted for corresponding elements. And such source can provide complementary higher X-ray energy regime than other lab sources. And also, since we have end stations, just like in the synchrotron, so this allows us to more operating space, and therefore combining with more complicated in situ setting is possible. And of course, there are some drawbacks. For example, currently we have a very big beam spot on the sample. We didn't do any X-ray focusing, and therefore more tricky data processing is needed. And also currently lower energy XAS, like 3D elements, it's not possible. And finally, we are mainly doing some ZEMs so far, and we haven't done too much XAS, and so that the XAS data still needs to be improved. Okay, so due to these like advantages, one of the potential is that this can be applied to in situ experiments where big operating space is required. So in addition to that, for in situ experiment, stability of the X-rays are required. The stability is controlled by specifically designed X-ray beam monitor. So this is X-ray, okay. So this is the X-ray beam without the monitor, and this is with the monitor. So basically the monitor cuts off a portion of the X-ray beam at the bottom. And this graph shows the source size and positions stability over roughly 3 hours. So it's quite stable. So now we are ready to go for in situ measurement tryout. This work was in collaboration with Technical Chemistry 2 group at TUM. And we are trying to observe a slow dynamic chemical species changes while ramping up the temperature inside the reaction cell. So here I show you, I hope you can see the video. I show you an accelerated video of the control panel. This video is playing a loop. So this panel here, it shows the temperature inside the reaction cell. And this one is a spec terminal, which is also used in many synchrotrons to control the experiments. And this is the picture that is captured on the CCD camera, and each exposure is 30 seconds. So for example, now we are looking at the sample palette inside the reaction cell, and we took 5 images. And then now it's the being without sample, and this one is a reference foil. Okay, so basically we are able to observe slow dynamics and are able to see some spectral changes when ramping up the temperature. Yeah, so yes, that's all of the work I want to show to you. So finally, I want to thank my colleagues and supervisors for this XAS work, and the technical supports from Lingshan Company for the inverse Compton scattering source. I also want to thank current MuCLS team and people from chemistry department for this in situ tryout. And finally, thank you for being here. And do you have any questions for the talk?
Okay, so thank you, Juanjuan. That was really awesome. Yeah, so if there are any questions, please type them in. I don't see any right now, but please. Actually, I have a question. something you didn't talk about, and that is access or who is using this and who can use this, and is there a model for that?
Okay, yes. So so I have a supporting slide for that. So currently at MuCLS, we don't, it's not like synchrotron, we don't have a proposal system for the beam time, and it's usually accessible to external users by being granted through collaborations with local groups. But of course, if anyone is interested in doing something, doing some collaboration work, and please also feel free to contact my supervisor, Martin, and Professor Franz Pfeiffer. So, yeah.
Okay, so also one of the potential advantages of a laboratory system is that you can run a sample or an experiment for, you know, a month at a time or several weeks at a time. And you showed one slide about stability. Do you have any, though, have you looked at doing any data where at lower concentrations, and if you build up statistics, does does noise cancel or, you know, get canceled out as you count for a low concentration sample for a week or so, or is there some other instability in the data collection?
You mean for XAS? How is the data statistics for lower concentration samples?
Or even for Zanes, if you go to lower concentration, can you go to low enough concentrations and just count for, you know, a month and have that be?
To be honest, I haven't tried that, but since this is in transmission mode, so I guess this is not suitable for samples whose concentration is very low, and I think, but other than that, I haven't really tried to see the differences, how the statistics are using different concentration of the sample. So far, I only tried measuring sample with optimum transmission signal. I haven't really tested it.
Okay. So Yulia has a question or two.
Yeah, hello, nice talk. So I'm kind of thinking in terms of time resolved experiment, and you said you can have like 60 picosecond pulses.
Yes.
So what is the rep rate, or what is the spacing between those pulses?
Okay, so for this inverse Compton scattering design, there are basically star ring design, and also there's a linear design. So the star ring design, we can reach a very high repetition rates, like 65 megahertz. So the repetition rate is very high, so that the photons we get, each pulse is actually very, very small. So I think but for linear, for inverse Compton scattering, which uses linear design, I think they have more photons per pulse. So far, I think ultra fast study at our source, it might be a bit challenging because the photons per pulse is just too little.
And so that stage ring, so you said the one which has bigger flux. So what is the pulse structure there?
I don't have the number here, but I think for the linear design, they have a lower repetition rate and more photons each pulse.
Yeah.
But I'm not sure about the exact values.
Okay, thank you.
Okay, Chengyun, you had a question?
Next talk, I was wondering what's the energy range of the facility and how many elements?
Okay, yeah, sure. So I changed back to these slides. So maybe I was talking too fast. So currently the energy range, X-ray energy range is from 15 to 35 keV. And this can cover these elements.
Okay, and Matthew has a question also, I think.
Yeah, it occurred to me that if you change the polarization of the laser beam, you would also then change the polarization of the X-ray beam. So I was wondering if there's any interest possibly in doing dichroic measurements or imaging.
I think it's possible to play around the polarization, but I'm not an expert in this source. So maybe Martin he can comment on that. Or
yeah, so essentially the X-ray beam should get the polarization from the laser. That's completely right. But and you could change the polarization of the laser, but this optical cavity also accepts or gets the best stored. So it's basically a passive amplifier, which also works best for a given polarization. So one would probably have to look more into that, how to run this also with other polarizations.
Okay, so in theory possible, in practice not really practical.
no. So far we yeah. So far I think with our facility it's not possible to do dichroism. Yeah.
Okay, so Tim, hi. Do you have a question about other similar facilities?
Yeah, sure. Sure, yeah, thanks. Nice talk. Just a very simple question. Is this a totally unique facility, or are there other similar or planned facilities anywhere else in the world?
Yes, there are also many other groups developing this kind of inverse Compton scattering source. However, our facility, I mean, currently it's the only commercial, the inverse Compton scattering source that we'll use is the only commercial prototype. So the other groups, I think there are many in developing phase, and yeah.
Thanks.
Okay, and Richard, you has a great question. Open-ended question. Please.
Yeah, I was just wondering how easy it is to operate a source. So is it more like an X-ray tube where you just switch it on and be happy, or more like a synchrotron? I guess something in between.
Yeah. So I mean, X-ray tube is a very major technique. So X-ray tube is really easy to use. But in this case, I think the operating difficulties again lying in between X-ray tube and large facilities. So, yeah. So Martin also again he has a lot of experience in operating the machine. Maybe he can also again share some his experience.
Yeah, I would agree to that. So it's somewhere in between. Well, I haven't ever operated the accelerator of a big synchrotron, so I don't know how involved that is. So it's an accelerator. It's not like a push button. So you have to tune up the accelerator, but you don't have to be an accelerator physicist to run it. So I think it's more like setting up an X-ray beamline at a synchrotron, I would say, from the complexity. So more like operating a beamline.
So currently, how much of the time is on this one hutch is using XAS or energy dispersive XAS, and how much is using other methods?
Okay, so yeah, so I think currently we have several people doing different projects with the source. So currently it's mainly me doing X-ray absorption spectroscopy, and so far we haven't, apart from this collaboration with chemistry group that I showed you before, we haven't got really other real application systems so far. So currently the beamline, and also during this lockdown, so currently the beamline is not very often used for X-ray absorption spectroscopy after all these proof and principle results that have been done. But I mean, the meantime, because we don't really have a proposal system, and it's mainly, so far it's mainly our own PhD students, our own people doing experiments on it. So it's always like very flexible regarding of beam time.
Right. So just out of curiosity, what is the majority of the time used for? Is that for like tomographic imaging?
Yes. So I can. So yes. So here I show you some major works in our group. Yeah, because we are X-ray biomedical imaging group. So there are a lot of imaging work which has been done using this source. And also, as I said before, like divergence is 4 millirad, and actually we didn't put any optics in it, and the beam is very homogeneous, for X-ray imaging. So far, there's a lot of full field X-ray imaging techniques which have been done with the source.
Right. Okay. Were there any other questions? I guess Morris had a question about polarization.
Yeah.
Also about polarization. Was that answered?
Basically,
Or
just
go ahead.
To follow up on the previous polarization question. So your light is polarized in a certain linear direction.
Yes, I think so.
So you could do dichroism by rotating the sample.
Wow. Yeah. I'm not sure whether this is feasible. I personally don't have experience of doing dichroism, so yeah, maybe it's possible. I'm not so sure.
Maybe just another unrelated question. That is, how expensive is the complete setup?
Okay. Yeah. This is a very commonly asked question. So I also again prepare a slide for that. So, yeah. So since it's a commercial system, so the investment for according to Lingshan Technology Company, so the cost is around a few % of a large synchrotron facility. And to have entire facility, also including not only the source, but also radiation shielding infrastructure and 2 end stations. And the cost for such a similar facility is around 12 to 18 million euro. But I mean, this can be this can be used for different purposes, imaging, spectroscopy, and so on.
Yes, thanks.
Seems completely reasonable. Okay, are there any other questions? I don't see any. So, and we're about at the time. So let's all thank Juanjuan again. That was really impressive stuff and amazing